Okay, so number 40, I said, is a kind of a challenging problem. And so we'll come back to this one. You can solve this one at home. So number 40, we're looking at the N2O4 NO2 equilibrium. And so we have N2O4 gas going to 2NO2 gas. And they give us a Kc value for this. Kc is 4.61 times 10 to the minus 3. And what we have is we already have an equilibrium situation. This is at equilibrium here. And so at equilibrium, I'm going to have 0.971 moles. This in the brown is at equilibrium. 0.971 moles of N2O4 over 0.75 liters. And so what's the molarity of that, since we're dealing with Kc? So there's 0.971 divided by 0.75. And so it's 1.294. So this is going to be 1.294 molar here. And then the NO2 is 0.058 divided by 0.75. And that gives me 0.07733 molar. Now I have 3 sig figs. I'm going to carry an extra digit because I want to check the ratio here. Let's check the Q ratio. If we check the Q ratio, then it should match K. We should be at the proper ratio if this is at equilibrium. And so this is going to be 0.07733 squared. So I'll just go ahead and do that. 0.07733 squared. And then divided by 1.294. 1.294. That gives me 4.62. This gives me 4.621 times 10 to the minus 3. Am I really at equilibrium? If I was at equilibrium, this ratio should match K. Take a look at my Q ratio. Does it match K? It doesn't, so they're saying it's at equilibrium. Okay, the N2O4 NO2 equilibrium mixture in the flask on the left, they're telling me this is at equilibrium, but when I look at the Q and K don't match. Now, this is what happens. This is why I carry extra digits. So why I carry extra digits is why don't they match? Tell me, because they just told me that's equilibrium. They don't match because, 1, we're really not at equilibrium, or 2, because of round-off error. They're very close, right? But they aren't the same. They aren't the same because this is not at equilibrium, or they aren't the same because this is round-off error, what we consider round-off error. Because this is round-off error. If I carried all the digits out, then they should match, but I didn't bother carrying all the digits out in the calculator. They should have matched. Or there's round-off error in the given data. And so, this is close to a match. And so we're going to say that this is equilibrium. Now we're going to perturb the equilibrium. How do we perturb the equilibrium? We increase the volume. If we increase the volume, an increase in volume by Le Chatelier says it's going to favor which side? It favors the side with more moles of gas. So it should shift it to the right. And so we're going to perturb it. When we perturb it, we're going to screw it up. It's no longer going to be at equilibrium. And so now I'm going to have 0.971 moles, but now the volume is not 0.75. The volume is going to be 0.75 plus 2.25. And so what we'll do is, this is a valve here. We open the valve, and then it goes over there. And so now it's going to be over 3.00 liters. And so the new molarity, the new initial molarity is 0.971 divided by 3, which gives me 0.3236 molar. Okay, and then over here I have 0.0580 moles over the new volume, 3.00 liters. And so this is going to give me 0.058 divided by 3, which gives me 0.01933 molar here. And so these are my new. Now let's check the K value here. So, I mean, not the K, the Q, and compare it to the K. And so the Q value is going to be this squared, so 0.01933 squared divided by 0.3236. And I get 1.15. 1.154 times 10 to the minus 3. Now take a look. Our Q is way off. The ratio is way off now, right? Because the volume changed. Now the ratio is way off. The ratio has to go bigger. Do you see my ratio is too small? The ratio's got to go bigger. That means I need more product. And so the change we see, if Q is less than K, the shift is to the right. And so we're going to have minus X. We already predicted this based on Le Chatelier's. Le Chatelier's says increase in volume favors the side with more moles of gas. And so this is going to be plus 2X here molar. And so at equilibrium, I'm going to have 0.3236 minus X and 0.01933 plus 2X. And then I just plug this in to my Kc. The Kc is going to be the NO2 squared over the N2O4 concentration. And so this gives me 0.01933 plus 2X quantity squared divided by 0.3236 minus X. Do you like binomials? Do you want to get this into quadratic form and use the quadratic equation to solve it? We have two choices. We can get this into quadratic form, use the quadratic equation to solve it, or we could do guess and check, you know? Which one's faster? I don't know. Both are going to take some time, right? And so this is okay that we solve for X here. But there's a way to minimize the number of binomials. What's one way of minimizing the number of binomials? Well, you know, what would be helpful is spend, like, if you have a little bit of time before class, just flip through your notes from the previous day or previous few days, and then you know, I get a feeling, then you'll know more what I'm asking. But here, one way of getting fewer binomials is by resetting. You know, that was one of the purposes for resetting. And so this is the math. It's solvable. This is not impossible. It's just time consuming. This is just time consuming. But it's not hard because it's just a binomial. It's getting it into, you know, multiplying out binomials and then adding things and doing whatever else. It's not hard. But on a test, you have a limited amount of time. You have like an hour and a half. How much time do you want to spend doing the algebra, right? And so one of the tricks here is this. Okay, this is my original ice table. And I know that if I reset, by resetting, I'm not really going to upset anything. I mean, it still should work. And so what I'm going to do is I'm going to reset the initial conditions. These are my initial. Now, I could reset it to the right or I could reset it to the left. When I look at the K, that tells me which direction I should reset it. Which side is the equilibrium favored? On the left or the right side? Look at the K ratio. In other words, it's 10 to the minus 3. So is that 1 over 1,000 or is that 1,000 over 1 if I have 10 to the minus 3? 10 to the minus 3 is 1 over 1,000 or 1,000 over 1? 1 over 1,000. So this is product on the top. This is reactant on the bottom. Which side is favored? Reactant side would be favored. So what I do is I reset it left to favor the reactant. And so what I'm going to do is I'm just going to do this because the math is, I don't want to do this much math. And so what I'll try to do is this. I'm going to take my original initials. Actually, let's do that. And so I'll just rewrite this up here. I'll take my original initials. The original initials is 0.3236 molar, 0.01933 molar, and then I'm going to reset this. And so I'm going to move everything to the left. So this is plus y, this is minus 2y. And I'm going to move everything, but I have to watch out for limiting reagents. In this case, there's no limiting reagent. And so this is, I'm going to lose all of this, so I'm going to move all the atoms over here. And so the new initials, this would be the reset initials, are going to be this. So I just have to take half of that. And so what is half of 0.01933 divided by 2? And so, and then add it to that. And so this is going to be plus 3236. And so I'm going to get 0.33326 molar here. And now the change has to be, because if I look at Q, Q is 0, because product over reactants is going to give me 0, it's got to go bigger. And so this is going to be minus x molar, this is going to be plus 2x molar. And so I'm going to get 0.3332 minus x molar, 2x molar. Now look at what happens to the math over here. What happens to the math is this. So this is just going to be 2x quantity squared divided by 0.3332 minus x. Now, which one's going to be easier to get into quadratic form? The reset one or the original one? The reset one's going to be much easier to get into quadratic form. Plug this into your quadratic equation and then you're done, right? And so we do that, but there's one other thing we could try,